So we're going to continue work on this section. I'm not hurrying with this chapter. It is different. And I like to, well, do another exercise that deals with this geometric series. So geometric series deals with the summation notation and infinite number of terms. So we have to just put a few terms and then dot, 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 so it doesn't get cut at some point. It continues forever. That's a big difference, right? So let me do, say, problem number 61. It has geometric series, and it wants us to deal with the summation from 1 to infinity. 1 to infinity, that's for the coefficient that we have here called as a letter K. So 5, which I can keep on the outside, it has nothing to do with this series. What we have is part that relates to this coefficient, which is K. So we have a quarter raised to the power of K minus 1. So 1 less than we have K. What does this mean? Well, this is geometric series. You don't have to do this, but you can see what we're actually producing by getting K's when K is actually equal to 1. So our quarter will be raised to the power of 1 minus 1, which is going to be a 0, right? So if I put inside K number 1. So if you have a 0 power, then it is always equal to 1, right? So I'm talking about is taking quarter and raising it to the power of 0. I hope you already aware that this is always equal to 1. So no matter what number you raise to the power of 0, it's always going to give you the same thing. It's always going to be 1. So that's why I don't really care for this term. It is 1 that I multiply by 5. So the next term will be 5 multiplied by 1/4. So if I add, 5 is staying on the outside, but now we get that same 1/4 is raised to the power of the second term, so it's 2 minus 1. And 2 minus 1 will give us just 1, right? First power. And I will be multiplying this by 1/4, then that number 5 by 1/4. So it looks like we're producing the next term using ratio 1/4. So whatever is raised to the power is our ratio because it changes. You just keep multiplying by that. So ratio R is found. And then you produce the next term if you multiply 1/4 by another 1/4 and so forth. So we do have plus dot, dot, dot geometric series. And for that matter, we need to know the first term. And I think it is 1. When you say, Alex, it's 5. Well, if I factor 5 out here in front, then it's just 1. So I need to use the formula for that sum, which is fraction A, first term is on the top, and 1 minus R is on the bottom. And this formula works because my ratio is less than 1, right? Because if it's more than 1, this formula is not what we use because there'll be infinite sum. So I'm gonna use the formula and keep 5 the way it is. Then have on the top a, which is 1. A is on the top, and 1 minus 1/4 is on the bottom. So this is my answer. So when you subtract 1 and 1/4, you get 3/4. That's right. You can always think of 1 as 4/4, right? $1, 4/4. So from 4/4, you subtract 3/4. So you're gonna end up with 3/4. And then 5 is multiplied, so I can put it on the top, and we can get rid of this complex fraction, because this 3/4 is the part that bothers me really. So I need its denominator to be gone, and to make denominator disappear, I will multiply by this denominator, so it cancels. And I also have to multiply the top of fraction by this, so I actually times fraction by 4/4. It doesn't change the fraction, but it cancels my denominator and get 20 on the top and 3 on the bottom. So there are all kinds of answers here. So write down this sum, and this is what we were supposed to do. We found sum of this series, it's 20/3, and we purely used abstract approach. We use formulas, so I guess we got the answer, and that's pretty interesting, right? So we need to have our series, we have ratio less than 1. That's very important, because otherwise terms are gonna increase and increase and increase and not gonna get smaller, and that's important to realize. Like, for example, in exercise 59, notice that terms are increasing. You add 12 and you add bigger number. So if you start to think about the ratio of these terms, if you divide 12 by 8 ratio, you always divide the previous term into the following, you get number 4/3. Actually 3/2, you divide by 4, 3/2, and it's more than 1. Since it's greater than 1, the sum of series is not going to be finite, it'd be infinite. So we say it's a divergent series. Or we can say the sum is not finite, infinite. Same thing, but ratio has to be less than 1. That's important. So you can try another exercise if you want to over weekend. That'd be a long weekend because tomorrow is a big holiday, right? It's the 4th of July. So I told you there'd be, in spirit of holiday, no class on Friday. So this Friday, you don't need to worry about math. You can just enjoy a long weekend, 4th of July. You didn't have any plans, maybe you can do it. So just give it a break. And like that, as promised. So no class. And we'll pick it up again next week on Monday. We'll keep working on chapter 12. In fact, I'd like to start a little bit of chapter 12, section 4, a very different section that's called mathematical induction. So what is this for? Well, it actually enables you to prove things that we don't really Well, we didn't do many proofs in this class. In fact, in math, we took pretty much everything for granted, but at some point, they start to do proofs like in linear algebra class, if you decide to take that one, which is being taught in our school. There are some proofs appear. In calculus, we also have some proofs. It depends on instructors. Some instructors get into them, some don't, but we do have proofs. And proofs are always being done for the sets that we cannot put our hands on. Because if you have, say, a set of 10 elements, then there is nothing to prove because these elements are all in front of you. You can see everything that's going on. But if you have infinitely many elements, like in the sequences that we just worked with, there are infinitely many. We cannot see all of them because they're infinite. So we just can't. There are too many. So we need to prove something to be able to make statements. And that's what mathematical induction is actually used in. So what it does, it proves various formulas for infinite sets. What does that mean? Let me say, here's the formula for set up to n, but n can be any number. N can be 1 billion, n can be 100 billion, and so forth. So for any n, that's the power of it. So we have infinitely many formulas because n can take on infinitely many values. So when you don't have finite number of elements, when you say, Alex, it's finite, it's n. Yes, but there are not finite number of these n's. See, the n could be trillion, whatever. You just have infinitely many possibilities. That's why to prove it for all of those values of n, we have to use that special method, or maybe some other methods that you might learn later. But this is a very popular in the case if you can count your elements. So if your elements is like first, second, third, fourth, and they just keep going and going, start at some place and go infinitely. It's just like we have here with series also start somewhere and go infinitely. So we keep going and we don't miss any elements. And that's the key idea. So we don't miss anything. We just start at 1 and we never miss. We just keep going all the way to n. So that method is being used in this case. And the method actually says the following. There are two conditions must work. First, it has to work for 1. So usually people, if they trying to prove something for n, then they don't use n, they use k. That's style. We already saw this before. So it has to work for k equal to 1, because we're trying to prove from beginning all the way to element n. So that's the ending place. But k is not n. K could be 2, 3, 4, 5. So it is different. N is the last one. And well, to check if it works for 1 is not hard. You just look at the first element and it's in front of you. The second condition is different. If works for if, see, that's a logical setting. If works for everything before, it works for all less than k. They put this with a special type of inequality. So they say here, statement works for k. It also works for the next, for k plus 1. Works for all elements less than k, or they say just for k, which is equivalent, then see it's like a logical statement if, and then you use then, it works for the next, which is k plus 1. Then it works. It works for k plus 1. But it's kind of, one can say, obvious, because if you start at element number 1, the first element, and then you have everything's fine for the first element, whatever. What is everything? Well, it could be any formula that you're trying to prove. It's very abstract. So it works for first element. Since we have a working for first element, then it has to work for second. We use k plus 1. So that's then automatically working for second from the second condition. Then it has to work for the next element, because if it's working for second, it has to work for third, and then it has to work for fourth, and for fifth, and for sixth, and so forth, and etc. See, key idea is that those elements can be arranged, the first and then second, so that's how they actually justify this proof. So if it starts to work for first, like dominoes, you push one, then it hits the next, hits the next, hits the next, and that way it hits all of them, so they're all gonna lie down. So that's how they justify this, and that's interesting. So the goal for today is just to have a little flavor to see how you could possibly use this in proving things. And all you do is you test first element, and then you need to see what happens with k plus 1. So that's how they do this, and they can maybe go over this particular example one to see what's going on. So, for instance, if you're working with some kind of formula, so they're trying to prove that this works for all ints. So if you add all these elements, it's going to be n squared. So what does that mean? Well, if you start adding numbers 1, 2, 3, 5, it's not going to be n squared, but you can see what this is if you, for example, try 1 squared. So method says test it for 1. So that's the first condition. It has to work for 1. How does it work for 1? Well, if n is 1, it's 1 squared, right? So what numbers should you add to get 1 squared? Well, you need to see what 2n minus 1 is, right? What would be the last number? Well, if you replace here 1 instead of n, why do I do this? Well, because I work with n equal to 1. So I'm trying to add numbers all the way to 2n minus 1. So I need to see what's the last number. So if I put 1 here, instead of n, it'll be 2 times 1, 2 minus 1, it's 1. So how many numbers do I add? Well, the last one has to be 1. So I start at 1, and I have it as a last number. So I don't
Oh. He's like, he got disconnected.
Did you disconnect or?
Yeah, it seems like he got disconnected.
Okay, so I just wanted to finish up with this example and let you go, so since we started. So how this whole process works, we first of all check and see if it works for n equals to 1. So if you put 1 here, and if you put 1 here in the formula and see if it works, then you end up with a 1 here, right? So 2 times 1 is 2 minus 1 is 1. So the last number is 1, the first number is 1. So you actually end up with 1 on the left side, and on the right side of this formula is 1 squared. And all you need to see is that, yes, it is working. So now you need to check it for k plus 1. So that's what they say, k plus 1. So you need to take this formula and see if you add numbers 1 and 3 and 5. So bunch of odd numbers added all the way to 2 times. Instead of n, you have to put k plus 1, right? Because that's what we trying to test. So instead of n, I put k plus 1 and then subtract 1. And what my goal will be is to see if this is going to be equal to, again, I put instead of n, k plus 1. So that's what we're trying to see if it's working. And how can I see that? Well, I guess I need to simplify my left side and the right side. So the left side is going to have something that goes to 2k plus 2. That with my last term, right? So 1 plus 3 plus dot dot dot. And we end up with the last term, which is how we're trying to put dots. 2k plus 2 when I distribute, but it's a good idea to always see what's before 2k plus 2. So what's going to be before? When you say, oh, it looks like, oh, it's 2k plus 2 and minus 1. So it'll be 2k plus 2, but minus 1 is 2k plus 1, right? So what's before? Well, it looks like it's going to be the previous odd number, which is 2k minus 1, isn't it? Let me see. Are you sure? Well, because if you have odd numbers here that are being added, 1, 3, 5, next will be 7, next will be 9. To move back, I need to subtract 2. 5 minus 2 is 3. 3 minus 2 is 1. So if I drop 2 here, so 1 subtracts and then another one. So it will be 2k minus 1. And the previous will be 2k minus 3. So that's what my left side looks like. And what's the right side? Well, on the right side, I have to multiply this k plus 1 with a k plus 1 because it's squared, isn't it? So how can I do this? Well, I guess I need to just distribute. Right? Write this parentheses with this internet outage. Again, panicked. Was running around the apartment back and forth, and eventually turned on. I don't know if that helped though, but I've been doing it, so it's made me feel not very well. So anyways, when you multiply, notice if you FOIL the terms inside and outside, right? They're usually same. So k and then the k. So if I add these, there'll be 2 k's, right? And then plus 1. Because the product of 2 terms. So this is the goal. And the goal is to show that this sum is indeed equal to that, right? Just simplified word. Are they equal? And they have to be because of this. Remember, the method of induction says if you have something that works for case of k, and for the case of k, you go all the way to k. So the last will be 2k minus 1. Just like in the formula. Then it must be equal to k squared, right? So let us add. So that's true. That's what's given. They gave us. It works for k. What does it mean? Well, put k in the formula and you get a true statement. So then what I do is add on both sides exact same thing, and looks like that same thing will be 2k plus 1. So if I add 2k plus 1 on the right side, and if I add exact same 2k plus 1 on the left side of my equation does not get changed, which means it's still going to be true. And if I do this addition, guess what I'm going to get? I'm going to get exactly what we need to prove because I add this 2k minus 1 on the left side, and I add 2k plus 1. 2k plus 1 on the left side and 2k plus 1 on the right side. And that's exactly what I need to prove. So we say it's proved. And that's what they explained here in example 1. So I would recommend you to read this, because I know it's not obvious. You see this first time, it's kind of questionable. But the idea is to make sure that you realize that if this equation number 3, they put 3 here, works, then adding on both sides, whatever, as long as it's the same thing, adding 2k plus 1 on the left and on the right, that's what they do. It's also going to work, like adding 1 on both sides of the equation, or 5 on both sides, or 2k plus 1. It's still going to work. And it means that what we need is working. So if works for k, then it works for k plus 1. So if it works for previous, it works for next. So how can we call them? We say k and k plus 1. If it works for k plus 1, it works for k plus 2. works for previous, works for next, and so forth and so forth. So it works for everything. And that's the usage of this method, to show that it works for all of these countable terms. So you can count 1, 2, 3. So it works for all of them. So you just show it works for first, and then it works for next. And then it works for next, for next, for next, for next, and then works for everything. That's the idea behind this method. So next time I will do some exercises using this, and next time will be on Monday, not Friday. Friday will be, I guess, a long weekend, and I will be working on this internet as well. So not really long weekend for me, but I hope I will be done with it. And now we're going to have a little break. So happy 4th of July. Thank you for being patient and still being here. And those people that left, it's fine, because I'm gonna email this recording a little later today. So have a good day, and
Thank you, Professor.
thank you for coming. Bye-bye.
Yeah, of course. Have a good 4th of July and enjoy your long weekend.
Thank you. Appreciate it.